For our final exam review here, our first question is about determining whether we have a function based off of graph using the vertical line test. Clearly, if we put a vertical line on here, we're going to hit 2 points, one here, one here. So if we hit these 2 points, it is not a function. So this is not a function. Y is a function of x because one x would result in 2 separate y values. And that's what the vertical line test does for you. In this question, we're determining y as a function of x based off the equation. If you want to solve this equation for y, we would get x plus 9 equals y squared, and then we would take the positive and negative square root of x plus 9, and that would be what y equals. And so looking at this, this is how you determine whether y is a function of x. In this case, do we plug in 1x and get 1y? And that would be a no because of the plus and minus. So no, this does not define y as a function of x because 1x would give you 2 y values. Here, if we want to determine the domain and range, first the domain is about what x's we could plug in here that would give us a particular y value. In this case, x plus 6 has to be greater than or equal to 0 so that we don't get a negative, which should tell me x has to be greater than or equal to negative 6. So here's your domain. The range would then be what values you would come out of that. One easy way to see what the range would be to think about the graph of this function. If you think about the graph of this function, it would be 6 units to the left at -6. That goes along with this domain. And it would look like this. The y values that are constructed using to construct this graph would be your range. Notice the smallest y value is at 0, and then every other y value would increase from there. So the range would be y greater than or equal to 0. Here, if we want to evaluate the function at f of a plus 3, we plug a plus 3 into the function for x. So f of a plus 3 would be a plus 3 squared plus 3, in which case we would get a squared plus 6a plus 9 plus 3, and we would get a squared plus 6a plus 12. In this, we want to find the difference quotient, so we would have to figure out what g of x plus h is first, which would be 5 times x plus h squared plus 9 times x plus h plus 5, in which case we would get 5 times x squared plus 2xh plus h squared plus 9x plus 9h plus 5, giving us then finally 5x squared plus 10xh plus 5h squared plus 9x plus 9h plus 5. Now that's your g of x plus h. Here's your g of x using the difference quotient formula. Our difference quotient can be found using g of x plus h minus g of x all over h. So we're going to take this, subtract this from that, and divide by h. So that would give us 5x squared plus 10xh plus 5h squared plus 9x plus 9h plus 5 minus 5x squared plus 9x plus 5, or minus 5. Sorry, everything here is based off of this being a minus 5, minus 5, minus 5, minus 5, minus 5, minus 5, okay? All over h. So then if you look at what happens here, negative distributes into here. We're going to have a minus 5x squared. That'll cancel with this positive 5x squared. This will give us a minus 9x, cancel with this positive 9x. This would give us a positive 5 because of the double negatives, and this is a minus 5 here, so they would cancel. So what would that give us? That would give us 10xh plus 5h squared plus 9h all over h. Every term here in the numerator has an h in it, so if I factor an h out, I could get 10x plus 5h plus 9 all over h. That allows these two h's to cancel, giving me simply 10x plus 5h plus 9. There's your difference quotient. Here we want to graph this piecewise function. we have these two pieces, -4 and -x minus 1. This one, we're using x is greater than or equal to 1. This one, we're using x is less than 1. Here's 1 right here. So if we're using 1 as our value to start with, for x is greater than or equal to 1, -4 is the function, which would be this horizontal line here at 4. Okay? And we're going to include that value right there. Then for x is less than -1, we're going to use this as our function. Well, this is a line. It's a line that has a y-intercept of -1 and a slope of -1. So if you have a y-intercept of -1 and you have a slope of -1, which would be down 1 to the right 1, that would put us right here. And our graph would look like this for x is less than 1. So we're going to draw these two lines. We're going to use these x's for one line, these x for the other line. The break in the line is right here at this 1. Okay. So if that's the break in our line, you see that we have an open circle on this one. We'll have a closed circle here because here we're equal to 1. Here we're not. We're strictly less than. It passes the vertical line test right there, and then everywhere else also passes the vertical line test. So there's our piecewise function. Here we want to write the equation for the graph of the square root that's translated 2 units to the right. So that would be 2 units to the right. We would have to subtract 2 on the inside, and that would be 2 units to the right. Here we want to draw the graph of y equals x squared, stretched by a factor of 9, and the resulting graph is reflected across the x-axis. So if we're stretching it by 9, we're going to multiply it by 9. And if we're going to flip it over the x-axis, we're going to multiply the function by a negative, thus flipping it over the x-axis. Here we want to graph y equals the absolute value of x, stretched by a factor of 5.9, reflected across the x-axis, so very similar to what we did before, and then shifted 0.55 units downward. So just like in the previous question, multiply by negative and 5.9, and then we're going to, after that's happened, now we're going to shift it down 0.55 units. So we're going to subtract 0.55 from the function itself. Here we want to find the inverse of this function. First off, we have to make sure that this is a one-to-one function. Since they specified the domain is only x less than or equal to 0, then you see graphically that we have a parabola down 10 units. That's the x squared minus 10, which would normally be this. But since we're only using x's less than or equal to 0, which would be these x's here, this whole branch of the graph does not exist. So if we're only working with the left-hand branch of the parabola, you can see clearly that this piece is one-to-one. It would pass both the vertical and horizontal line tests, so it is a one-to-one function. So now what we're going to do is we're going to replace f of x with y. We're going to solve for x. So we'll take the square root, and here normally when you take the square root, we'd want the positive and negative square root. But that's where this is going to come in. X is less than or equal to 0. X is going to be negative or 0, which means we do not want the positive root. We want x to be negative. So now we're going to switch the roles of x and y. So we are going to get negative square root of x plus 10 equals y. And there is our inverse. Okay, here we need to find measures of this angle, one positive, one negative, that are coterminal. Coterminal means 360 degrees from this angle. So I take 76 degrees minus 360 degrees, and I'll take 76 degrees plus 360 degrees. And those would be my two coterminal angles, one positive and one negative. So if we take 76 minus 360, we would get negative 284, and that would be degrees. And then if we took 76 plus 360, we would get 436 degrees. Make sure you put your degree measure on here because when you measure an angle, you have to state how you measured it, degrees or radians. And if it's degrees, you need the degrees symbol or you need to write degrees. So we want to determine whether these two angles are coterminal with one another. Well, if their difference is a multiple of 2 pi, which in radians would be a complete rotation around the circle, then they would be coterminal. So 13 pi over 3 minus pi over 3 would give me 12 pi over 3. And 12 pi over 3 would be the same thing as 4 pi. Well, 4 pi is a multiple. It's 2 times 2 pi. So it's a multiple of 2 pi, so it's 2 full rotations. So the idea here is here's pi over 3. If I drew it more accurately, it would probably be more like that. There's pi over 3. And then the idea here is if I go one full rotation around and then another full rotation around, that's where 13 pi over 3 would fall. So this would be 13 pi over 3 as well as pi over 3 would be this same terminal side. So here we want to convert this radian to degrees. So in order to do that, we take our radian measure, 11 pi over 12, and we'll multiply by 180 over pi. So we cancel the pi's. Here we could simplify the 180 and the 12. We would get 15, so that we have 11 times 15. So once we do 11 times 15, we get 165 degrees. So here we want to find the measure of the arc length. The arc length is the distance around the outside of the circle. So we want to find this distance here. The way we find that is by using this formula, S equals R times theta. The key to using this formula is theta has to be in radians. If theta is not in radians, you need to convert it to radians. Well, this is in radian measure. So we would use the radius, which is 16, times the radian measure, which is pi over 3. Okay, and the distance would be measured in inches because the radius is in inches. So we would get 16 pi over 3 inches. If you would convert that to a decimal and round the 2 decimal place, you would get 16 times pi which would be about 50, and then you would divide by 3, and you would get roughly 16 point, with 2 decimal places, 16.76 inches. Here we want to use the exact value of this function. Again, without using a calculator. Calculator lots of times will give you an estimated decimal answer. We want the exact value. So looking at this, we would need to know what the sine of pi fourths is, and we should know that the sine of pi fourths is square root of 2 over 2. So then it's a matter of figuring out where does 7 pi fourths fall into. Well, 7 pi fourths, if we compare that to 8 pi fourths, 7 pi fourths is clearly 1 pi fourth smaller. 8 pi fourths you should know is 2 pi. So you should know 2 pi is 1 full rotation, so that would be 8 pi fourths. So we then back that up, pi fourths, I would put 7 pi fourths in quadrant 4. So here's 7 pi fourths would be this rotation to here. So quadrant 4, we would look at the y value in quadrant 4, which should be negative. So then the sine of 7 pi fourths based off of the sine of pi fourths should be negative square root of 2 over 2. Do the same here. We should know that the cosine of pi sixths is going to be square root of 3 over 2. So then we use that to help us find the cosine of minus 7 pi sixths. So again, if you think of 7 pi sixths, we should know that 6 pi sixths is the same as pi. So 7 pi 6 should be pi 6 further than that, but it's negative. So now we're going to go 1 pi 6 more in the rotation clockwise than 6 pi 6. So if you think about here, this would be negative 6 pi 6. Then if we go another pi 6 further than that, that should be what 7 pi 6, negative 7 pi 6 looks like. That would put us in quadrant 2. X values in quadrant 2 are negative. So if that's the case here, then knowing pi 6 and knowing my answer should be negative, cosine of negative 7 pi 6 should be negative square root of 3 over 2. So here we want to use a reference angle to find this expression. The key is figure out 780 and what angle it's related to. Well, it's coterminal to one of our special angles. So if we look at this, we take 780 and we subtract 360 from it. We're going to get 420. Then if we subtract 360 again, you're going to get 60. Okay? So 780 and 60 are coterminal to one another. So if I can find the cosine of 60 degrees, that should be the same as the cosine of 780 degrees. Well, we should all know this cosine of 60 degrees is 1/2. So there's our answer. Okay, here we want to find the sine of alpha given that the cosine of alpha is 2/3. So we know that sine squared alpha plus cosine squared alpha equals 1. So sine squared alpha plus 2/3 squared should equal 1. So sine squared alpha should equal 1 minus 4/9, which would be 2/3 squared. Move to the other side, so I subtract it. So then sine squared alpha should be equal to 5/9. Now to figure out what sine equals, we'd have to get rid of the square, so we'll take the square root, but when we do, we need the positive and negative square root of 5/9, which would be plus or minus square root of 5 over 3, square root numerator denominator. Now the question is, well, is it positive or negative? Well, that's where this comes in. Sine of alpha is greater than 0, so the sine of alpha, we don't need the negative, it's greater than 0, so we should get positive square root of 5 over 3. Here we want to find the amplitude. The way you do that here, it should be A sine of bx minus c plus d is your standard form for the graphing of a sine, and A, or specifically the absolute value of A, is going to give you your amplitude. So in this case, it's -2. So the absolute value of that would be 2. So the amplitude is 2. Remember, the negative doesn't do anything to stretch the function. The negative would just flip this over the x-axis. It's how far are we stretching the graph vertically to then put our new range values in place. Okay, so if we want to graph the cosine function here, there's two things happening with this cosine function. We have an amplitude and we have a phase shift. So to deal with the amplitude, it's very simple. We're going to set our amplitude of 3/4, so our range is going to be between positive 3/4 and negative 3/4. Let's ignore some of this markings here. Let's just, so we have some space, let's call this 3/4 right here, and let's call this one negative 3/4, so that we have this sort of marking of where our range is going to be. Then our phase shift of pi/3. So remember our original starting point for cosine was at 0. So we'll set that x minus pi/3 equal to 0, and it was also ending at 2 pi. So we'll set this equal to 2 pi, and right away when you solve these, you see that x equals pi/3, and here you're going to see x equals 7 pi/3. So our graph is going to extend out to start at pi/3 and end at 7 pi/3. If we cut that directly in half, you see we're going to get 4 pi/3. If we then cut each of those in half, we're going to end up getting 5 pi/6. and we're going to get 11 pi sixths. So these are where our key points are going to go. So our cosine starts up high. We're going to hit the x-axis at 5 pi 6. We're going to reach our minimum at 4 pi thirds. We're going to hit the x-axis again, 11 pi sixths. And then we're going to come up to our maximum again at 7 pi thirds. And so this would be our one period of our cosine graph. Okay? And then that's going to continue on and on and on and on for forever here as it goes. But our key points here, this one would be pi thirds is the x coordinate. This one would be 5 pi sixths, 5 pi sixths. This one, the minimum would be at the next value of 4 pi thirds. Here we'd hit the x-axis again. That would be at 11 pi sixths. And then we end the period at 7 pi thirds. For this sine function, all we have is a phase shift of pi thirds, and we can use a lot of the same values as before. So we're going to start at pi thirds. We're going to end at 7 pi thirds. If we cut that in half, the middle would be at 4 pi thirds. Cut each of those in half to get our other key points. Remember, there's 5 key points here. This would be 5 pi sixths, and this would be 11 pi sixths. And the way you always do it is you add these together, divide by 2, that would give you this. Add these together, divide by 2, that would give you this. So if we set up our graph, the range is still -1 to 1 because our amplitude is still 1. We start at, let's cross these out. Let's go with some new values. Let's say here's pi thirds. We'll end off at 7 pi thirds. So let's call it here just so we have some space. Here in the middle, we'll call this 4 pi thirds. Here, this one in between the two of these, here, this will be 5 pi sixths. And this one here in between would be 11 pi sixths. So we think about how our key points work for a sine graph. We have x-intercept, x-intercept, x-intercept. Then we have maximum, and we have our minimum. So if we then put the sine graph in there, using these values, that would be one period. We would then repeat that over and over and over again throughout the graph. But our key points would be pi thirds, 5 pi 6, 4 pi thirds, 11 pi 6, and 7 pi thirds. Okay? So here we want to graph the sine function shifted pi 12ths to the right, stretched by a factor of 7, translated 2 units downward, then reflected across the x-axis. And this is a big key. It's reflected across the x-axis last. So thinking about it, if we're going to translate the unit 2 units down, so we have something that we're going to move 2 units down, okay? Then we're going to flip that over the x-axis. That's going to then put it 2 units up, all right? So thinking about that, the graph being 2 units up instead of 2 units down, that's going to make a big difference. So if we did this based off of the steps it told us to follow, stretch by a factor of 7, we're going to multiply it by 7. We're going to shift it 12 units to the right, so that would be x minus 12. Pi 12, sorry, pi 12 units to the right. Okay. Then what we're going to do is we want to translate it 2 units down and reflect it over the x-axis. So reflecting over the x-axis multiplied by negative, but remember, 2 units down, then followed by reflection would actually be 2 units up. So we'll do a plus 2 there. Here we want to find the exact value of tan of 5 pi thirds. Again, if we know the tan of pi thirds, which we should all know at this point, the tan of pi thirds should be square root of 3. Then we should be able to do 5 pi thirds, as long as you know where 5 pi thirds falls. Well, compare 5 pi thirds to 6 pi thirds. Clearly this one's smaller, but 6 pi thirds is 2 pi. So this is pi thirds smaller than this one. So if that's the case, we have 2 pi. Go pi thirds back from there. That's where 5 pi thirds should fall. Quadrant 4, this is 5 pi thirds. Tan in quadrant 4, if we're using y over x, should be negative over negative, which would give us, or sorry, negative over positive, should give us a negative overall. So in that case, this should be negative square root of 3. Here we want to evaluate secant squared of 2 theta if theta is pi 12. So we'll just plug it in, see what you get. Secant squared of 2 times pi 12ths would give you secant squared of pi 6. Remember, this is the same thing as saying the secant of pi 6 all squared. So we just need to be able to do the secant of pi 6. Well, again, if you know the cosine of pi 6, then you should be able to do the secant of pi 6. Because the cosine of pi 6 we should all know to be square root of 3 over 2. So the secant of pi 6 should be the reciprocal of that, 2 over the square root of 3. So then if we do 2 over the square root of 3 and then square that, you see we're going to get 4 over 3. Square the 2, square the square root, and you get 4/3. All right, so here we're going to graph the tan function. If you remember, the tan function typically has this shape to it, where we have a vertical asymptote on either side. One would be at pi halves, and the other one would be at minus pi halves. Ignore these values here. So what we have to do is figure out how is this going to change. Well, this is going to change the period and the amplitude. Period and the phase shift. Here the amplitude is 3/5, and if we stretch out this thing or compress it with that 3/5, in this case we would compress it, it's really not going to make a huge difference in that. It's not changing our range. So we're going to largely ignore the 3/5 as our amplitude change. It's not really going to make a huge difference in our graphing, but the 1/3 x plus pi fourths is again a period change and a phase shift. So our original vertical asymptote was at minus pi halves and positive pi halves. So we're going to have to use this as our basis for finding the new vertical asymptotes. So if we solve this, we're going to get 1/3 x equals negative 3 pi fourths, and then that would tell us that x equals negative 9 pi fourths. And then here, if we solve this, this will give us 1/3 x equals pi fourths, and therefore x equals 3 pi fourths. So here's our new vertical asymptotes. Now to find the x-intercept directly in between them, we add these together and divide by 2, so then our x-intercept would then be at negative 3 pi fourths. So if we put all that together, we have negative 9 pi fourths as one vertical asymptote. We're going to have negative 3 pi fourths as our x-intercept. And then we're going to have positive 3 pi fourths as our other vertical asymptote. So here's just the y-axis. Here's the x-axis. And then so our tan graph would look like this in between. But then remember, that's going to replicate itself over and over and over again throughout. But mainly we just have to draw the one period here, and you see in one period, that's what your tan function will look like. So the graph of y equals tan x is shifted a distance of pi 12ths to the right, stretched by a factor of 7, translated 8 units upward, then reflected in the x-axis. So again, 8 units up, then reflected over the x-axis. Since this reflection is happening last, we go 8 units up and then reflect that over the x-axis. That actually puts us 8 units down. Okay? So overall, we want to write the equation of a graph that's 8 units down, not 8 units up. So we have our tan. It's stretched by a factor of 7. We're pi 12ths to the right, so x minus pi 12ths. Okay. Reflected over the x-axis and 8 upward. Since the 8 was up first, you actually remember we're 8 down, and the reflection is the negative out in front. So arctan of 1. When we want to find the arctan of 1, we want to figure out what angle that would be equal to. Well, it's the same thing as saying the tan of some angle gives us 1. Now remember, our requirements here are that our angle has to be between minus pi halves and positive pi halves. So What angle between minus pi halves and plus pi halves would give you 1? Well, we should all know that if that angle was pi fourths, the x and the y coordinates would both be square root of 2 over 2, positive in either case, and tangent being y over x would give us 1. So pi fourths is the answer. That's the angle between negative pi halves and plus pi halves that would give us the tan of 1. Same thing with this one. You got to think what angle, when I take the sine of it, do I get square root of 3 over 2? That angle, again, has to be between minus pi halves and plus pi halves. So right away, you should know that the answer is pi thirds. So here what we want to do is we want to be able to evaluate this composition. Now, since we're taking the sine of the arctan, these don't cancel each other out, so we would have to take the arctan of 2 first. So you have the sine of the arctan of 2. We'd have to first take the arctan of 2. So we have to figure out what angle is that going to be. And then, that's just, remember, because that's the same thing as saying the tan of theta equals 2. And then we're going to have to take the sine of that angle. Well, this isn't just a straightforward question where you say, oh, we got a special angle. So instead, what we could do is we could draw this picture. We could say, okay, here's theta. We know the tan of theta is 2. We could also write as 2 over 1. So we could say this is 2, this is 1. We could then say the Pythagorean theorem would give us the third side. So a squared plus b squared equals c squared. So this would be then the square root of 5. And therefore, we would get the sine of theta to then be opposite over hypotenuse. And since this was essentially the same thing as the sine of theta, because the arctan of 2 should be theta, we would get 2 over square root of 5. Or if you were to rationalize that, you could also write it as 2 square root of 5 over 5. Here we want to find the secant of theta. If you remember, for secant, you should know that it is going to be hypotenuse over the adjacent side, okay? Because it's the reciprocal of cosine. So in that case, we have everything we need, and it would be 26 over 10. If you then simplify that, they're both divisible by 2, so you would get 13 over 5. Here we have a terminal side of an angle where the point on that terminal side is 21, 28. And we want to figure out what the sine of this angle is. So in order to do that, we need a couple of measurements. We need the y coordinate, and we need this radius here, this distance from the origin. Well, we can say that this is a right triangle. The x coordinate being 21 means this side's 21 and this side's 28. So we could say 21 squared plus 28 squared equals r squared, or r equals the square root of 21 squared plus 28 squared, which would then give us, we would get 35. So now knowing that r is 35, we can find the sine of theta by doing y over r. So we get 28 over 35. Well, clearly that's able to be simplified. Okay, we have 7 can go into both of those, so we get 4/5. So here we want to use some identities to simplify this expression. A couple things I'm going to do. I'm going to factor out the cotangent of x, and that would give me 1 minus cosecant squared x all over tan to the negative x, tan of negative x. You also have to know that tan is an odd function, so I have cotangent x over actually negative tan x, being that tan is the odd function, and I still have 1 minus cosecant squared x. Okay, then you're going to use one of your Pythagorean identities to take care of the cosecant squared. So you should know that 1 minus cosecant squared should be equal to your cotangent squared. Okay, so these are just identities that we should know at this point. So remember your three Pythagorean identities. One is that sine squared plus cosine squared equals 1. Another one is that 1 plus tan squared equals secant squared. And then 1 plus cotan squared equals cosecant squared. So in this case, we're going to use that 1 plus cotangent squared equals cosecant squared to help simplify this piece. So again, remember 1 plus cotangent squared equals cosecant squared x. So we don't quite have that here, but if I switch the cosecant squared to that side and the cotangent to that side, I'd subtract each one. So we could say that this piece here would be equal to negative cotangent squared. Okay. So what do we have here? We have cotan x times negative cotangent squared x all over negative tan x. So we can say that these two negatives are going to cancel each other. Then what I can say is that tan x is really the same thing as a cotangent. So 1 over tan x is cotangent. So I really have a cotan x. I have a cotan squared x, and I have another cotangent x, technically with this 1 over tangent here. So ultimately what I have is I have cotan to the 4th x would be the way I can simplify this all the way. I'll do the same with this one. I'm going to factor out a sine w. That would leave me with cosine squared w plus sine squared w all over cosecant w. Well, we should know that cosine squared plus sine squared equals 1. So then I could just say this is sine w over cosecant w. But 1 over cosecant w, I can say it's the same thing as sine. So I have sine w times sine w, and then therefore giving me sine squared w. Okay, here I want to find all real numbers in the interval 0 to 2 pi that satisfy the equation. In order to do that, I'm going to factor out a cosine x, giving me 2 sine x plus 1 equals 0. Now I'm going to use the zero product property. Two things multiplied together equal to 0. Cosine x equals 0, or 2 sine x plus 1 equals 0. So here, I just got to figure out what x I can use here. That would give me 0. Here it's sine x equals negative a half. And what x would give me negative a half when I take the sine of it? I got to figure out the angles that are between 0 and 2 pi that satisfy this. So here, there are two angles that would satisfy cosine x equals 0. That would be when x equals pi halves and 3 pi halves. And what angles would satisfy sine x equaling negative a half? So that would be multiples of pi 6. That would be negative when you take the sine of them. So that would put me in quadrant 3 and 4. So that would be 7 pi 6 and 11 pi 6. So those four angles are angles that would satisfy this equation here between 0 and 2 pi. So here, looking at this, we have a triangle we're trying to solve. Looking at what we're given an angle, a side, and an angle. So angle, side, angle, we're going to use law of sines. We could solve for this angle right here first. If we did 180 minus 26 minus 51, that would tell us what that angle is. That would give us 103 degrees. 103 degrees. And then if we call this one, say B, and this one, say A, and this one, say C, I know it's gamma, but let's say C, this would be side C, this would be side A, side B. So we use the sine of A over A equals the sine of B over B equals the sine of C over C. To solve this, knowing what side C and angle C are, that's what we're going to base this off of. So again, we're going to use the sine of 103 degrees over 20. Let's work with B first, should equal the sine of 51 degrees over B. We could also say the sine of 103 over 20 equals the sine of 26 degrees over A. And then we can use these both to solve for A and solve for B. So in this case, if we solve for B, we would find that B should equal 20 times the sine of 51 all over the sine of 103. And here A should equal 20 times the sine of 26 degrees over the sine of 103 degrees. So for B, if you do the calculation, you find it's about 15.95. And for A, if you do the calculation, you would get about 8.998, so let's round it to 9 even. Okay, here, if you notice what we have here is we have side angle side. So side angle side, we're going to have to now use the law of cosines to solve this. So one of the first things I can do is, if I call this angle C, is I can find side C. So I'm going to use the fact that C squared equals A squared plus B squared minus 2AB cosine of C. Here we're going to call this one A, we're going to call this one B. So if we did that, we would say C equals the square root of 7.7 squared plus 11.11 squared minus 2 times 7.7 times 11.11 times the cosine of 116.5 degrees. And that'll give us side C. So from that, I get C to be 16.10 with rounding. So that's my measure for side C. So now I got to find alpha and beta. Well, that's where we're going to use first. We're going to use the A squared equals B squared plus C squared minus 2BC cosine of A. We'll call that alpha. Okay. Now we got to solve for alpha here, so we got to rewrite this equation. So we're going to start dumping things to the other side. So another way I could write this is going to be the arc cosine of A squared minus B squared minus C squared divided by the negative 2BC. And so filling in everything we have, we know A, B, and C, which are the sides of the triangle. We could say arc cosine of A, which is 7.7 squared, minus B squared, so it'll be 11.11 squared, minus C squared, which is now 16.10 squared, over negative 2 times 7.7 times no, sorry, not 7.7. It would be 11.11 B and C. So it would be 11.11 times 16.10. So you put that in your calculator, you would find out what alpha is. And we would do the same thing with beta. We would use the B squared formula, which ultimately, if we solve for beta, we would get the arc cosine of B squared minus A squared minus C squared over negative 2AC. to be the answer for our beta. So here we would say beta equals the arc cosine of 11.11 squared minus 7.7 squared minus 16.10 squared over negative 2 times 7.7 times 16.10. And so beta would equal our calculations there. So if we plug each into our calculator, we would get, so for alpha, I would get 25.33 degrees. And beta would give me 38.12. Now remember, all your angles in your triangle have to add up to 180. Now since these two are roughly rounded, so might not get exactly 180, but alpha plus beta plus this c, which would be the 116.5, should get us really close to 180. So 116.5 plus 25.33 plus 38.12 gets me to 179.95, which is really close to 180. I didn't get exactly 180 again because I rounded these, but that should give you an idea of whether or not your alpha and your betas are correct.